So suppose this is a RF receiver, and it's receiving some kind of power. So in system, when we send in signal, of course there will be some noise as well. So signal to noise ratio is it's a ratio of power in case of the signal power and noise power. So signal to noise ratio is signal power and noise power. So if it's in case of input power, input signal power, input noise power. So, and if we're calculating at the output, and it is output signal power over output noise power. So this is the signal to noise ratio, that is SNR. So it is the ratio of desired signal power to undesired noise power. So this is our desired signal power, this is our undesired noise power. So and then hence we can see that it is dependent on the power. So when noise and desired signal is applied to the input of a noiseless network, both noise and signal will be attenuated or amplified by the same factor, so that the signal to noise ratio will be unchanged. So however, if the network is noisy, the output noise power will be increased more than the output signal power, so that the output signal to noise ratio will be reduced. So then we need to find out this noise figure, and noise figure is a measure of this reduction in signal to noise ratio. So because of this, in case of noisy network, when we are sending our desired signal power, and this output noise power will be increased more than our desired output signal power. So noise figure is a measure of this reduction in signal to noise ratio, and this can be calculated as signal to SNR of input over SNR of output, and it must be greater than or equal to 1. So input noise power is the noise power resulting from a masked register. And this can be calculated as Ni equal to K T naught B. K is Boltzmann constant, T is temperature, and B is I'm not sure, we will know later. Okay, B is bandwidth here. B is bandwidth. So then usually in a normal condition, T naught is equal to 290 Kelvin. So suppose this is a circuit, and there is a resistor, and there is a noisy network, and from this noisy network we have to pass the signal power to the output R. So input signal power would be desired signal power plus input noise power, and we will get the output power as desired signal power and plus desired noise power, output noise power. So network is characterized by this gain, bandwidth B, and equivalent, which is noise temperature TE. So output noise power is equal to amplified input noise, that is, this is amplified input noise plus internally generated noise. So output noise power is equal to the amplified input noise plus internally generated noise, and that can be calculated as N naught is equal to output NO, or N naught you can say. Output noise power is the amplified input noise plus internally generated noise. The output signal power would be S naught is equal to G into SI. G is the gain. So input signal power is multiplied with gain, and then we get the output signal power. We have the output noise power, output signal power, and then we can again apply the same in the noise figure we have here. This noise figure, the noise figure is the calculation of the reduction in this SNR when compared to the input to the output. So in decibel, if we want to calculate the noise figure in decibel, then we need to apply this formula, 10 log after calculating value, and which should be must be greater than equal to 0. So if the network were noiseless, this TE equivalent temperature would be 0, so giving noise figure equal to 1 or 0 dB. So solving for TE, we get TE equal to, since this we get from here, this, so I think this is from this, F equal to 1 plus T E over T naught. So I think we can understand this, which goes F minus 1 equal to T E over T naught, hence resulting T E is equal to T naught F minus 1. So this is this. So now there are two types of components, linear and non-linear, right? So let's talk about this response of non-linear components. We know this non-linear components equation can be written as the response can be written as it has this, it increases, it's not linear. From the equation you can observe this, because of this it's not linear, right? So then we get this formula. This is just the normal mathematical calculations. And so in case of amplifier, is it linear or non-linear? So amplifier, I think, because it's not though it passes through the origin, but it's not a straight line, because it's bending from here in some kind of operational frequency or operating power. So this, though it has a linear region, but it's not linear component, because it's not linear, its whole result is not linear. So this is not linear component, this is a non-linear component. Then the low noise amplifier is a compromise between the gain and noise. Between the gain, the low L and A, I think you have heard this name if you have been studying RF frequency. So the low noise amplifier is a compromise between the gain and the noise. In other words, like if gain of the LN is sacrificed for noise, hence we definitely need more gain with the image frequency amplifier. And there are some questions, and okay, then let's talk about super heterodyne receiver. There are two kind of receiver: direct receiver and super heterodyne receiver. Although I think there are more than those, but the two typical commonly used are direct receiver and the super heterodyne receiver. This is a structural example of super heterodyne receiver because it has two basebands. It has IF filter. The difference from direct receiver is about this super heterodyne is because of this image filter after the signal is mixed. So if you want to know about these linear elements, you can look at this. It will clearly explain what is the linear elements and the non-linear elements, because it does not have this linear straight line that is passing through the origin. That means the non-linear relationship between the excitation and the response, whereas in case of linear elements it has a really linear linear relationship between the excitation and the response. So that's all for today. Finally, just remember that the characteristic curve of a linear element will follow only one equation of the straight line and will pass through the origin for all the values of time. So every linear element must exhibit bidirectional property, and vice versa is not true. Thank you.